Okay, Nanjan, we can start. 7.5, we can start.
Okay. Is my screen visible?
Yes, visible.
Okay.
Whenever you want to ask question, you can unmute the student. That option is there. Okay, you can unmute.
Yes. Yes.
I will
Okay,
unmute.
so
Then after half an hour, I will handle the session. You just handle it.
Okay, so welcome back once again. So we'll start from today the advanced part of NLP. Okay, so till now what we have discussed the general ML algorithms and the basic NLP task, how to solve these basic NLP tasks using ML. So from today onwards, we will start the advanced part, which will use deep learning and particularly neural network and various types of neural network to solve NLP problems. So today we are going to discuss about the neural network, basics of neural network, how neural network is being trained, what is it, and also we'll see one demo how to train a neural network with using some library. Okay, so to understand the neural network, we have to see a function. So we know what is a function. Generally, let's start with this function. Generally, the idea of a function is it can be viewed as a machine. So this is a kind of machine that takes an input x and transforms. This function is actually transforming the input x and produces some output y. Okay, and maybe the function can take one input. Let's say the function can be just like this, adding one. Just you give one input 2 and it is just transforming that input by adding 1, or the function can be a square of the input. So that means what is a function? A function is a kind of machine which will take an input and transform it by using some kind of transformation like adding or squaring or anything, and it will produce an output. Okay, so if when we plot a function, we can easily plot it in x-axis. We are plotting the input, and in the y-axis we are plotting the output. So this is for this function. When we plot input versus output, these are the points, and we combine the points, you will get a line, straight line. And for this one, it is a curve like function. Okay, now consider, instead of taking one input, consider a function which will take two inputs. One is x, another one is w, and the function is just multiplying these two input, that is x into w, and it will produce an output. Let's call it y cap. Okay, and let's say the x is fixed. That means we fix the x. Let's say it is 3, which cannot be changed. Only thing we can change is the w. Okay, now when we put different w, we'll get different y cap. Okay, but how we have a target value, let's call it 10, and let's say it is the y. That means I want to find out what will be the w for this x value 3. X value 3 is fixed. I have to find out what will be the w, so that the output, which is y cap of that function, is equal to the actual output, that is target, that is y, which is equal to 10. How will do that? Let's intuitively do it. Let's put, that means what we need? We need that our function output y cap to match the target value to get as close as possible. Let's take y as 1. When we put y as 1, what will the output? Output will be 3. Now, if you see, our objective is that the output should be 10. But when I take w equal to 1, it gives me output as 3. Okay, that means what is the difference? The difference is -7. That means when we take w equal to 1, the output is off by -7. Okay, let's change it. But what we need? We need that the output should be equal to the target. So let's adjust it. Let's put it 3. So when we put w as a 3, what will the output? Output will be 9. Now it is close to my target, that is 10. But still it is off by -1. Let's change another w. Let's adjust it to 4. If we put 4, the output is 12. Now it is overshooting the 10 because previously it was 9 for 3. Now it is 10. That means best W value which will be between 3 and 4. So let's make it 3.2. So when we make it 3.2, the output will be 9.6 and it is very close to 10. Is it okay? And this process of doing changing the W for getting the accurate Y, this process is called the learning. What we are doing, we are learning the value of W. Okay, and this is nothing but this is the concept behind the neural network learning. Let's see what is X. Generally, X in our case in the neural network or machine learning, we call it as features. So we have different features. Let's say we will have only one feature, that is X. So X value is given. That's why I have fixed X. X value will be given. And also this W is called the weight associated with that input. And your target is Y is the target. And in the supervised learning scenario, the Y is already given. For particular X, you know what is Y. For this input or this feature, this is the actual output Y. Okay. So how actually we are learning W or the that function? So first what we'll do, the process is very simple. First what we'll do, set W to some random initial value. So we are initializing this W to some random value, then calculate the difference of this function output and the actual target. Okay, and now decide how much to change W so that the target will be equal to our prediction value. Okay, so now what you will do, you update W, again go back to step 2, again you calculate the difference between these Y cap and Y, and again you see how much is the difference. If it is close, it's okay. If it is not, again you have to go back and again change the W. So when to stop? Now you just keep doing this until there are two conditions. Either one condition met, you will stop. One, that some condition is met, that is the difference between the function output and the target is below a certain threshold. Let's say I say if the difference is below 0.4, then it's okay for me. It may not be 0, so we can stop. Or another stopping criteria is that when we'll do a certain number of attempts, means this repetition, let's say we'll do only 10 repetitions of this updation. Okay, now this process conceptually we call it as neural network learning. That means here W is actually going to be learned. Your feature is given, you know the actual target, you have to find out what will be the W so that the output of the function is close to the actual target. Okay, so conceptually this is how neural network get trained or and work. Okay, is there any doubt on this part? Okay, so let's see, let's put it in another way. So let's say this is the function. I'm putting that circle as the function X into W. Okay, and what it takes input X, and this W, let's call it weight of that input. That means how much importance this X has. So that weight will decide the importance of X. Okay, and this function is X into W, and it is giving Y cap. Okay, so but what is the problem with this? If we use this as a function to learn some mapping from input to output, here we are trying to map X to Y is the actual output. We want to map input feature X to output target Y, and we have decided the function is X into W. Okay, and for what W, that Y will be equal to Y cap, that we have to find out. But if you use this function, you will see there are two problems. What are they? Number one, that this function only describes a straight line which pass through origin. You know what is the equation of a line passing through origin? Y equal to mx. So here Y equal to nothing but W into X. So in place of M we have X, W. X is your variable. So now if you, just for illustration purpose, if you take W equal to 1, so the line will be like this. This is the function for W equal to 1, that is X. Okay, but think a scenario. You have to classify that there are two class of points. Some class are green, some class points are blue. That means we have to find out a line that best separate these two classes, so that any point above the line will become green, any point below the line will become your blue. But if I use this function, then what will be the possible lines? Now you see, if this is the function, what it will be. So let's say y is either green is 0 or 1 is blue. Okay. So now if w, you take w equal to 1, now this will be the line, because it is always pass through origin, x into w always pass through origin. So this will be the line. And you see, this line cannot separate perfectly, it cannot separate this blue and green. If I change w, let's make it w as a 2. Still, as it is passing through origin, still it cannot segregate this blue and green dots or green data points. So what is the problem here? The problem only here is that whatever w you take, it cannot create a line here in this area. Why? Because it is passing through origin. So that means this function what we are taking is not a good function for this. So what we can do? So this is difficult to find good fit. Why? Because the y-intercept, this y-intercept is stock at origin, that is in 0. So if I change the y-intercept, means if I change the y-intercept here, if a line pass through here, so then I can say that line can segregate these two. So for that, what we need? We have to add a bias term with this function. So now just introduce a bias b to translate the line up and down. This b will be the y-intercept. This will be, b is increasing positive, it will go up, b is negative, it will go down. Okay. Now, instead of finding out what is the best w to take that line which will segregate these two classes, we have to find out what will be the best w as well as corresponding b. What will be these two values, so that we get a line which will segregate the two classes properly. Okay. So now this is the case. So if I take b equal to 2 and w equal to 0.5, then this line will be created, and this line can be called as a class boundary, which can decide that anything above this line will be green, anything below this line will be blue. So that means we have to adjust not only w but also b to find a good fit which will segregate these two classes properly. Okay, so now my function is, instead of using only x and w, we have to add a bias term. Okay, so now you see, still this is one problem we have solved. One problem is that if I take x into w, the problem is it only goes through origin. So for this kind of data set, it is difficult to segregate them into two classes. So we need that bias term. But still there is a problem. Second problem is, still this describes a linear relationship between these two. That means if the data point are like that, if it is distributed like this in this space, and if it is linearly separable, means a line can segregate them, then this function is good. But generally in practice you may not get this kind of data set. If you got this kind of data set, where even if you take any w and b, whatever thing you do, this will give a line, but any line cannot segregate it properly, because the line should be like this curve, it should not be a straight line. Okay, so for that what we need, how we can change that line which is produced by x into w plus b into a curve like structure, or into a nonlinear structure, because this is not a linear structure, it is not linear. Okay, so what we'll do, now you see, bias alone is not enough, we need something else to help model these nonlinear relations, because these between these two classes the relationship is not linear. That means it cannot be segregated by a line. We need some curve like structure, some nonlinearity is required. So to add nonlinearity which will be able to segregate these two classes perfectly, what we have to do, we have to add in another function after this one, we call it as activation function. So let's say previously it was x is input, w is the weight of that, and we pass through this function x into w plus b. Let's say it is giving a output h. Now this h cannot solve our problem because it gives a straight line. So what I need, this value must be passed through another function. Let's call it phi. So here the function phi is a nonlinear function that transform this linearity into nonlinearity, so that a curve line can fit and it can easily segregate these two classes. So do we call this nonlinear function as a nonlinear activation function. Okay, so there are basically different activation functions are there. You can use sigmoid for this phi. You can use sigmoid function or a tan h function or a ReLU function. What sigmoid will do? Sigmoid will transform whatever is the output, whatever value you got from this function, this h, it will transform this h between 0 and 1, any value between 0 and 1. Okay. Now, tan h, what it will do? It will transform the value between -1 and 1. ReLU will do what? ReLU will find out the maximum. If it is negative, it will become 0. If it is positive, that positive value, that is maximum of this 0 and h will be outputted. So that means now if you use, instead of using this function ln, if I add a nonlinearity above that function, then easily I can fit it. Let's see. Previously, the bias ln is not sufficient. When I add this nonlinearity or nonlinear activation function phi, now you see it enables us to model this nonlinear relationship. It creates a best possible curve which will segregate them into two different classes. Is it okay? Now, what I need the input feature must be first transformed into this function. Now, output of this function will pass through a nonlinear activation function, which will, why we need it? This is required if your data set does not have a linear relationship. If it is nonlinear, then you must have to pass through this nonlinear activation function, which will capture this nonlinearity and produce a better prediction. Okay. Now, what is the building block? Now, for creating a neural network, we need one building block which will take input. First, it will transform them into x into w plus b. Then, whatever value it is obtained, it will pass through the nonlinear activation function. Then, we will get the prediction output. Okay. So, instead of using two different things, we can put these two into one simple picture. So here x and w is input. Now the first half of this circle will do this summation. So what is summation? Summation is x into w. Okay. So x into w, there may be many x and many w, so that will be done by here. Okay. Here b is not considered, only x into w. Okay. Now this part is a phi. Whatever output you obtain after this summation, you will pass this output to this phi, that is your nonlinear activation, then it will give you output. Then what is b? So your b will be like this. Instead of adding b, you just take b as input. You take another input like b. So b can become another input. Okay. So what it will be? Now this is called a neuron. So in a neural network, this is the neuron and this work is done by the neuron. What it is doing? A neuron is nothing but it consisting of two separate functions. First part of the function, whatever input it is getting, it is just aggregating. What is aggregating means? X into w plus this input is b, so it will aggregating x into w plus b. Okay, whatever output you are getting from this aggregation, that will pass to the second half of the function, that is second function, that is nonlinear function, and you will get the output. So this structure is called unit. Sometimes we call it as a node, and most famously it is called a neuron. So in a neural network, these are nothing but these neurons are interconnected to form a network. And what is their job? Their job is just these two operations. First, whatever input you give with its weights, it will be aggregated. Then the value of the output will be passed through a nonlinear activation, and that will be the output. Okay. So instead of taking one input, if you have multiple features, means more than one feature. So your input is x is nothing but the feature which is given in your data set. Let's say you have multiple features, three features here, x1, x2, x3. And each feature has their corresponding w1, w2 and w3. That means this w1 and w2 and w3 will provide us the information that which feature is how much importance in the output y. Okay, so if x1 feature is very much important in calculation of the output y cap, then we have to increase this w1. Let's say if w3 is less important, means sorry, x3 is less important in calculation of y cap, then w3 will become very low. Okay, so let's say there is a question. Suppose the green and the blue points are somewhere above or below as given in the diagram with linearly separable regions, then How to decide bias. So see what Anurag is asking, that let me go to that picture. So if you are saying, if it is, how will decide where this bias will be? Okay, so this bias is going to be learned. That means we have to, like we have decided that for this W it is not appropriate. So we have to find out different W and B which will get this line perfect. So that you have to decide. Okay, now what we have done, we have manually guessing that this W, this B, this W, this B, but there is a proper method that we'll discuss. Okay, okay, is it okay, Anurag? Okay. So now you see, this is your what I'm saying, that these are the three features, x1, x2, x3. It, let's say if it is a house price prediction, x1 can be number of house, number of homes present in that house, rooms. This x2 can be the area, x3 can be something else. Okay. So depending on that, the W1, W2, W3, we need to decide. Okay. And B is the bias that is given as input. Now this all are inputted, and what this part is doing, this part is actually doing what? Now it will multiply x1 into w1, summation means plus x2 into w2 plus x3 into w3 plus this b as input. So it will give you a value. That value is passed to this activation function. Now the activation function will give me the output. Okay, so this is the general block diagram of a simple one neuron network. Okay, now how we are actually doing, so what is this summation is doing what? Now x into w plus b. Now you see here what we are doing, we are not writing, just to see this one. Just a minute. So just to see x into w plus b. So this x here represents all x1, x2 and x3. How it is representing? It is representing like this. Let's say x1 is 1, x1 is 1, x2 is 2, x3 is 3. So these three are given in terms of a vector. So for representing all input, generally we represent them in a vector x. Okay, this is all input. Now what is w? W is all w1, w2, w3. So here w1 is 4, w2 is 5 and w3 is 6. So this w1 is 4, 5 and 6. This is x1. Okay, now instead of individually multiplying, what you do, generally we put them in the vector form, and then we just multiply the just to do the vector multiplication. So it is 1 into 4 plus 2 into 5 plus 3 into 6 plus this bias b is 7. You give it, it will give one value. That value is passed through this phi and it will give you the output. Okay, so this is generally the calculation. So here, so what we are going to do, so now this is my summation is what? X into w plus b. So if you want to remove this b, instead of writing b, can I write in some different way? So I can rewrite it like this. So let's say instead of using b, let's make b as w0. Okay, and we will use 1 as input. So it is same. So this, instead of b, I am writing w0 and this is 1. So that means w1 into x1 plus w2 into x2 plus w3 into x3 plus w0 into 1. W0 into 1 means this b becomes w0, so also it is plus b. So if we write like this, now the function will be very simple. So what it will be? It will be only x into w. Plus b we have removed. Why? Because this x contains this 1. That means x has now 1, x1, x2, x3. This w is w0, w1, w2, w3. Is it okay? So that means we can compose this type of neuron into many neurons and it can create a network of neurons. Okay. So let's take this example. Let's say I have x1 and x2, two inputs. Okay. And how we are going to create a neural network. So let's say I have only two inputs, x1 and x2. Now this x1 and x2, it creates a layer. We call this as input layer. This one is called your input layer. Okay, and the input layer is just only your inputs. Okay, so here I have two inputs, so the input layer has only values x1 and x2. Now we have a neuron. So I have one neuron. That means what I am doing, I am getting the value of x1 to this neuron, x2 to this neuron, and I have a bias, this one. Already we know that bias value is 1, so it is there. and these connection have weights. So here I have not written weights, so it is W0, W1, W2 like this, and we'll see what will be the notation. Okay, so instead of using one neuron here, if I use multiple neurons, this one neuron, another neuron, and another neuron, to every neuron the input is provided. That means this x1 value is going to this neuron as well as this neuron as well as this neuron. X2 value is also going to this neuron, and this neuron, and this bias is also given to this one, and this one. But each, remember, each arrow which is connected, they have their own weights. The w's are different. So how many w's are here? So here 3, this is 1 2 3, and there are 3, so there are 9 connections. So each connection has 1 w, so it is 9 w's. Okay, so imagine what will be the function. Okay, and now this layer is called a hidden layer, and the hidden layer is connected as all connection from the previous layer is connecting to this hidden layer neurons. So we call it this connection as a dense connection or a fully connected layer. That means between input and there is an output layer. Between input layer and output layer, there can be many hidden layers. So here I have created one hidden layer, and in this hidden layer, the number of neurons I have decided as 3. So this 3 is called width of the layer. So the width of the layer means how many neurons are present in that layer. Okay, and there can be many hidden layers. Okay, now let's say this is one output layer, and here this is one neuron, and here also the bias is there. All the output of these three neurons will be connected to this output layer. So this layer we call it as output layer. Okay, so between input layer and output layer, you can have one hidden layer or as many possible hidden layers. That is up to you. You have to decide, and in each hidden layer how many neurons, that also your prerogative, you can decide. Okay, now you see, and after this it will give you some output y cap. You have your original y, then you can compare them. Okay, so this is a typical neural network. What are they? We have input layer, we have output layer, and we have a hidden layer. And this, if you increase the number of hidden layer, we call that the depth will increase. Depth of the neuron means number of hidden layers, number of layers. Okay, if number of layer increase, we can say the neural network has bigger depth. Width means in each layer, how many neurons are there, that will decide the width. Okay. Now, this neural network is called two-layer neural network. Now, there is a simple question: why it is a two-layer? Already we have created input layer, hidden layer, and mentioned input layer, hidden layer, and output layer. It is a three-layer. But generally, we call it as two-layer. Why? Because in input layer, these are not neurons. Remember this, very important concept. This input layer is not neurons. Only neurons are available from hidden layer to output layer. Output layer is also a neuron. These are only input values. But for our simplicity, we are putting them in a circle. But you see here, I have not marked any like this, summation and phi, because these are only values. These are the positions where it will take only values. So that's why there is only two layer of neurons. So we call it as two-layer network. Okay. If you have another hidden layer, it will become three-layer network. Is it okay? So this is a neural network. Okay. So actually in neural network, what happens? Same operation, like in one neuron, what happens? Same operation is happening here. And it is nothing but we call them a sequence of matrix operations. So here only we are doing matrix multiplication and addition, nothing else. Okay, and I will show you how we are doing it. Let's see. So let's take three values: x0, x1, and x2. What is x0? x0 is this one. What is x0? x0 is this one. One is your bias. Okay. So x0, you have x1, x2, two other features. The value are there. x0 is just one. Okay. Now, this is your W's present between input layer and first hidden layer. How many W's are there? 9 W's are there. Why 9 W's? Because you see how many connections. For one, there are 3 connections. For x1, there are 3 connections. For x2, there are 3 connections. So it is 9 connections. So each connection has one separate weight assigned to it. So there are 9 weights. And how I am representing the weights? W superscript 1 subscript 01. Superscript 1 subscript 02. So what does it mean? Let's put it. So you see, W superscript 1 0 3 is subscript. That means this is 1 and subscript is ij. So this 1 means what? So here this 1 is actually called the layer index, because you see this W1 means this one means these WR belongs to this first layer. Between input and first layer, these are the weights. So that's why all W their superscript is 1. That means all R belongs to the first layer. What is ij? Your I is from previous unit, J is to current layer unit. Unit means your neurons. So for IJ, let's say 03. 03 means this W is associated with 0. This is 0. This is 0th neuron. This is first neuron, the second neuron, because X0 is 1. So 0, 0 and 3. 3 means this one. So you see here, what is W01? W101 is this one, because this is 0 neuron, from 0 neuron to first neuron, 1 neuron. And in which layer? Now in 1 layer. So it is the superscript is 1. Superscript 1, subscript 01 means it is from 0th input to first hidden layer neuron. Okay. Similarly, W11. W11 means this one. This line is W11. So the weight of this line is W11. Means fast, from fast input to fast neuron in the layer. Similarly, here also same, W21, from 2 to 1. So it is W21. So and I am putting all this W in this column format. Similarly, this one also same, W102. 02 means for this one. So here, and when you multiply this, what you will get? You will get a 3 vector value. You see why? Because it is 1 cross 3. It is 3 cross 3. So it will become 1 cross 3. Okay. Oh, is there another question? We were taking bias as W0 and considered it as a part of X. Yes. Then why are we taking bias separately while combining units into a neural network? So see, why we are taking bias like this? Because it is not an input. Remember, if you create this means you will put here 1, what it will be? It will termed as input, but it is not input. Bias is always there. Sometimes you will see the neural network, the bias are not explicitly mentioned. That means implicitly you assume that the bias is there, even if it is not mentioned in the neural network. But for the first time, what we are doing, we are putting the bias, because without bias, what is the problem that we have seen? Without bias, you cannot shift the line, and also if you are putting a nonlinear, also bias is required. So for that reason, bias is, as it is not an input, so we are not putting here. Okay, so that's why we are putting separately here. Is it okay? Okay. So now when you multiply, that means what we are doing. Actually, what for this, if you see only this one, this is x1 into W01. Sorry, x0 into W01, x1 into W11, x2 into W21. Then it will pass through some nonlinearity and you will get to A1. So what is A1? You see what is A1? A1 is this one. What it is doing? X0 into W01, x0 is this one, x0 into W01 plus x1 into W11 plus x2 into W21. Then it pass through this phi and it will get A1. Similarly, what is A2? So A2 is like this. This A2, x02 into x0 into W02, x1 into W12, x2 into W22. Then it will pass through same activation, you will get A2, and similarly for A3. So that means A1, A2, A3, these are the vectors. What it contains? A1 is here. Actually, this is A1. Okay, this is A1, this is A2. Okay, and this is A3. Okay, so these are the output, and I am putting this output in this vector, because what we are doing simultaneously, we are not doing one by one. Is it okay? Now this is called your output of the first hidden layer. This A1, A2, A3 are the output of this hidden layer. Okay, now this output is again fed to another neuron in the output layer. Okay, so these weights, generally we are putting these weights as a column format. Sometimes you will see instead of W01, 11, 21, you will see 01, 11, 21 in this order. So if it is that, you just transpose it. Okay, So for simplicity, we are already transposed it so that it will be easier to understand. Okay. Now come to this second part. So first part is over. We got A1, A2, A3. What is A0? A0 is the bias. That is 1. Already 1 is there because always bias is 1. So now what we are going to do? This one is going to be multiplied with these 4 weights. What are these 4 weights? This weight is W201. Why W2? Because this 2 subscript 2, superscript 2 means these weights are for the layer 2. That's why it is 2. 0, 1 means coming from 0th neuron to going to fast neuron. So this is 0. So that's why 0, 1. This is fast neuron. So it is 1, 1, 2, 1, and 3, 1. Because in this output layer only we have 1. So it is 1. So now you just do the multiplication like similar matrix multiplication. What will get? You will get y cap. So this is the actual operation that is going on inside any neural network. Okay. So we call this kind of neural network as a feed forward neural network. Why? Because we are feeding the data and it is just going on forwarding by calculating these values, and we'll get the output. Is it okay? Is there any problem till now? Okay. So now you just see here. So here we have not put any activation function. Try to notice it. Here we have summation and activation. Both are there in this neuron. But in this neuron, in the output neuron, I have not mentioned any activation. No activation function in the output layer for this example. Is it okay? Now question is, if there is no activation function, already we know that every neuron must have a summation part, means aggregation, then nonlinear activation. But always activation is not required. Where it is required, where it is not required, let's see. Okay. So let's build a simple regression model. We'll do, because as it is a supervised learning algorithms, so we can do regression and classification. Let's do regression, then we'll do the classification. Okay. So let's build to predict a house price. Let's same house price prediction job. What I have two inputs, means two features. That is feature 1, x1, which will give you square footage, means footage, how many foot is the house size, and this is the number of bedroom. So these are the two features. So there are two input. Okay. What I am doing? I am creating a neural network. Means this two input is passed to this neural network where I have only one hidden layer, and in the hidden layer I have 3 neurons, and in the output layer I have only 1 neuron. Okay. Now you see what happens. How will do the calculation? Now initially these weights, this W0, this is W0, sorry, W1, this is W2, W1 superscript W1, superscript W2. So these weights we don't know. We have to find out these weights. Let's initialize these weights randomly. Okay. Now this activation, sorry, this summation. So here also we are not putting activation. So remember, generally in a regression case, we don't use any activation. Okay. So typically there is no activation function in the output layer for regression. In generally, because in regression we want to find out a value, any real number. Okay. For classification we need some kind of probability. So for probability we need this nonlinear activation. But here we don't need it. Okay. So remember, in generally in regression we don't put any activation in the output layer neuron. So now this is your output is predicted. So it will predict some price. You randomly initialize these W's because you don't know what W. What will be the best W? So this W you randomly initialize, then pass through this neural network, you will get output Y or Y cap. Okay. Now we have your real output. Let's say for first input, first row, you give, let's say first row contains square footage is 120, number of room is 2, and real house price is, let's say, 1 lakh, and your randomly, when you randomly initialize these weights, it is predicting, let's say, 60,000. Okay. Now that means there is a difference. So for that, what we'll do? You calculate the loss. Okay. Now once you calculate the loss, then question is what kind of loss function you should use, how to calculate the loss. So generally for regression case we use a mean squared error loss. So what is mean squared error loss? Very simple. You have yi cap, means there are n number of examples, n number of inputs. For each input, it will going to provide this network will going to provide one yi cap. Means for first input y1 you will give one output, and the corresponding original output is there. You subtract them, square them, and for every input you calculate this difference. This is the loss, and you just add them and get the aggregate, get the average, divided by n. So we call this as MSE loss. Okay. Now once you got the loss, the total loss on all data, then you can change the W. Now let's say we call this as batch mean squared error loss. Why? Instead of taking whole output or a whole set of data, we take a batch of data. Let's say the batch of data contains 3. Means initially I take first 3 examples or first 3 rows in the data set, and when I pass through these 3 rows in the data set one by one, I got 3 different prediction: 100, 200 and 300. But for these 3 data, I have the original value, original output, that is 250, 125 and 400. So what I'll do, I'll put this value here. So that means 100 minus 250 square plus 200 minus 125 square plus 300 minus 400 square divided by 3. So what will be the output? This is the error. 100 minus 250 square, 200 minus 125 square, 300 minus 400 square divided by 3, because there are 3 data. So you got, this is the error. So error is 12,708.3. Okay. Now what is our objective? Our objective is that the error should be minimum. That means this value, when the error will be 0, now when this output will be 250, this output will become 125, this output will become 400, then when we do this calculation, it will become 0. So our objective is that we have to make this loss 0. Okay, let's see how to do that. So goal is to adjust weights to minimize this value. So how we'll do that? Now we have to adjust these W values so that the loss will be minimum or 0. Generally we may not get 0, but it will be minimum. Okay. Besides this, other loss functions are there: mean absolute error and Hoover loss. If you have interest, you can go and check. So one loss is MSE. Okay. Now see. So what we are doing? We have inputs. We pass these inputs through these neural network. It produces predicted price. We have their actual price. Then we use this loss function to calculate the loss. Okay. Objective is to update these W values in such a way that the difference, the loss, will be minimum. Okay. So this pass. So here we have inputted put the MSE loss. So this one pass from left to right is called forward pass. Give the input, calculate the y cap, calculate the loss. We'll call it as a one forward pass. Okay. Now let's do similar thing with a classification. We are going to do a binary classification problem. Let's say it is a spam detection. So for spam detection, this may be the network. We may have not 2 input, we have many inputs. Okay, so let's say I am taking 2 and other inputs are there. There are also maybe connection, but I am not given mention this connection. Let's take there are 2 input. This is my hidden layer neurons. This is my output. So imagine, so here you see we have given pi, because in regression you may not give a activation in the output layer, but here we need. Okay, so output has an activation, and generally it is a sigmoid activation. Why sigmoid activation? Remember, always remember, if it is a binary classification problem and you are using one neuron in the output layer, then definitely you have to use sigmoid as the activation function. Okay, for these hidden layers, and general trend is to use ReLU activation function. Sigmoid cannot be used here. Okay, we generally use ReLU, but if it is a binary classification problem and you are using only one neuron as the output, so remember that you have to give sigmoid as the activation function. What sigmoid is doing? Sigmoid is converting the value of after this aggregation into between 0 and 1. It will give some probability. Okay, now you got some probability value here. After giving pi, you will get some probability value between 0 and 1. But this y output is 0 or 1. It is not a probability. Then how will calculate the loss? What kind of loss function here we should use? So let's see. So here, this is sigmoid. So here, the loss function, so your y cap is between 0 and 1. Because obviously this pi will convert your output of this sigma between 0 and 1. So let's see. And but your actual output is either 0 or 1, but you are getting between 0 and 1. So how will you calculate the loss? So you see the loss will be called cross entropy loss for binary. So generally we call it as a binary cross entropy loss. Okay. So what is the loss function here? It is minus 1 by n summation I equal to 1 to n yi log yi plus 1 minus yi log 1 minus yi cap. So you see how actually we are combining these two things simultaneously. Now easily you can understand. So these logarithms are the general natural logarithms. Now consider this yi. What is yi? Yi is the actual output. Actual output is either 0 or 1. Okay. But what is yi cap? Yi cap is between 0 and 1, any value, because your sigmoid will convert your value to a probability value between 0 and 1. But actual yi is your 0 or 1. So now if y becomes 1, let's say original y is 1. Now if original y is 1, now you see this portion is not going to be calculated. Why? Because 1 minus yi is 1, so 1 minus 1 is 0, so it will become 0. So only thing considering is this one. So 1 into whatever log of your prediction. Okay. Similarly, if y is 0, so if y is 0 means actual y is 0, then this yi becomes 0, so this will become 0, but it will become 1 minus 0 is 1, and this one only remaining, log of 1 minus yi cap. Okay. So for every data point, you calculate this and find out the average. Let's see one example. So let's say I have 4 data points. 4 data points, when it is passed through this network one by one, the output or the prediction is for first data point it is 0.9, second data point it is 0.3, third data point is 0.2. But the actual output y is 1 for first data point, 1 for second data point, 0 for third data point. Now using these two, how I will calculate the total loss for these 3 data points. So your n is 3. Okay. So now you see what I'm doing. So now log minus is there, log 0.9. Why? Because you see when this is 1, actual yi is 1. 1 means this portion will become 0. Now this portion will become 0. So when this portion will become 0, this will only remaining, that is 1 into log of yi cap is 0.9. So log of 0.9 plus similarly for this one, actual yi is 1. So this portion will become 0. So again it is log of 0.3. Now for this one, yi is 0. So 0 means this one will become 0. Okay. And this one to be calculated. So when this is calculated, 1 minus 0 is 1 into log of 1 minus yi cap is 0.2. So that is log of 1 minus 0.2. So what is total divided by 3? Because there are 3 data points. So when you calculate, you will get. So why the question is why we are putting negative? Because our objective is to convert this into such a way that we need to minimize it. Otherwise, if you don't put negative sign, we have to maximize the log likelihood. So to make minimization, it has a minimization problem. We are putting minus. Okay. Now you get the value is 1.53. So the total loss on these 3 data point is 1.53. If you see, this one is now means this difference is very close, because it's 0.9, it is 1, very close. Means somehow we can say it is correctly predicting. This one is also correctly predicting, very close, 0.2 to 0. But this one is not correctly predicting. That's why this error. Okay. So this is called the loss. So here, what is our goal? Goal is to adjust the weights W so that this loss value is to be minimized. Okay. So this is one. And also here, when we put this cross entropy loss here, this total is called your forward pass. Means you are passing the input, it is going through these neurons, getting the output prediction, and we have actual output, and we have the loss function, cross entropy, we are calculating loss. This total process is called forward pass, like we are doing in the regression. Same thing is here in the classification, only thing this one is changing here, the loss function is different, and in the output we are putting some activation. Okay. So now let's this is for binary classification. Let's create a multi-class classification, is more than 2. We have to classify a document into 3 classes. Okay. So this is very important, try to understand. So as we are going to create a neural network which will take some input feature and classify them between three classes. It's not two. So if it is three classes, so what we'll do? The first input layer, your input features x1, x2, x3, whatever is there. Then first I have hidden layer, one hidden layer. You can have multiple hidden layers. Let's use only one hidden layer. And now this is my output layer. So remember how many neurons you actually need to create for the output layer. So it depends on the number of classes. As this problem is a 3-class classification problem, so the output layer should have 3 neurons. This is you have to remember. Input and output is fixed, you cannot change. Input is how many features are there, that many input. Output is fixed. If it is a binary, output will be only one neuron. If it is multi-class, output will be as many classes. As it is 3-class, so it is 3. If it is a 5-class classification problem, so the output neuron, number of neuron in output layer should be 5. Okay, now as it is a classification, we have to provide what? The activation we have already discussed, but here I have not given any activation. But the activation, what activation we need, let's see. So after passing through where this without activation, it is creating Z1, Z2 and Z3. Remember this very carefully. Now the Z1, Z2, Z3 are just real numbers, but we need probability. So what I will do, I need some kind of activation function here, so that it will convert this Z1, Z2, Z3 into a probability distribution. So what activation function we are going to use? It is softmax. Okay, what is softmax? Softmax is a generalization of sigmoid. If it is a 1-class classification problem and you are using only one neuron at the output, so you bound to use sigmoid. But if you are using multi-class classification problem and there are more than one output or more than one class, so you have to use softmax as the activation function. What it will going to do? It will convert these 3 output into a probability distribution whose sum will be 1. Okay, so let's see. Now, what is softmax of Z1? Let's see. So this is the formula. Softmax of Zi equal to e to the power Zi divided by summation j equal to 1 to k e to the power Zi for I equal to 1 to k. Okay. Now, if you see, let's take 3 values. Let's say Z1 is 0.3, Z2 is 1.1, Z3 is 2. Let's say these are the output. After forward pass, you are getting these outputs. Okay. So let's calculate this denominator first. What is denominator? Summation j equal to 1 to 1 to k e to the power Zi. So e to the power Zi means e to the power Z1 is 0.3, e to the power Z2 is 1.1, e to the power Z3 is 0.2. When you calculate, you will get this 11.74 as the denominator. What is the numerator? What will be the softmax of Z1? So Z1 will be e to the power Z1 divided by 11.74. Z2 e to the power Z2, that is 1.1 divided by 11.74. E to the power Z3, that is e to the power 2 divided by 11.74. So you will get this as y cap. So here y cap is not one value because we need 3 classes. We have 3 classes. For each class, I need some probability. So when you calculate, you will get this value. Y cap as 0.11, 0.26, 0.63. When you add up them, it will give you 1. Okay. Is it okay? Now, just see. So what y cap? Y cap is nothing but a probability vector. What is that vector here? For this, it is 0.11, 0.26, 0.63. But what is y? So your y is just a value, either 0, that class name, either Z1, Z2 or Z3, whatever is the class. So I will do that. So what kind of loss function is going to use? So let's see. So here the loss function to be used as called categorical cross entropy. So in binary classification, you have to use binary cross entropy. If it is a multi-class classification, you have to use categorical cross entropy function. Okay, similar. The equation is almost same. So let's see. Let's say this is my prediction for 4 input values. For 4 data points, I got these predictions because Z1, Z2, Z3, when they are passed through softmax, it is producing this. First one is this one. For second data point, it is this. For third data point, it is this. For fourth data point, it is this. What is my actual output? The actual output, you have to convert them into one hot vector. So you have to convert actual y into one hot encoding. You know how to do one hot encoding. Okay, so you convert them into one hot encoding means only the positive class position will be 1, rest negative class will be 0. For positive class will be 1, rest negative class will be 0. So this is my one order encoding. Now we have to compare. So what will be the loss function here? So this is the loss function which is called categorical cross entropy. What is it? Yk k equal to 1 to k, yk log yk cap. Yk is the original output, that is 001. Yk cap is your predicted output, that is 0.11, 0.26, 0.63 for this data point. Okay. So when you multiply this one with this one, means you just do this calculation, what you will see? 0 into this plus 0 into this plus 1 into this. Sorry, is a log of this. 0 into log of this one, 0 into log of this one, 1 into log of 0.63. So when you do this, what will happen? Now you will get 0.46. But unnecessarily we are multiplying these two zeros. You know it? So we need to remove them. If we remove them, what will be my final function? So only final function is minus log yk cap. That means we can calculate just this for the positive class. For the negative class, already it is 0. So why we should calculate it? Don't need to calculate. So when we use this, so my final cross entropy, categorical cross entropy loss function is this one, minus 1 by n summation I equal to 1 to n log yk cap. Okay. So if you put calculate, this is like this. Means these two things is not required to calculate. 0.63 into 1, because this position is corresponding. Now this is middle position is 1, so this 0.55 is going to be multiplied with 1, rest will be 0. 0.7 will be multiplied with 1, 0.81 will be multiplied by 1 divided by n. N is 4 data points, so it is 4. So what is my loss? So loss is 0.98. So what is my goal? So here same goal. Goal is to adjust the W value so that this loss will be minimized. Is it okay? So these are the three scenarios, and use these three scenarios in any regression and classification task. Okay. So in regression it is okay, because in output only one neuron is required, but regression means only one value to be predicted. And but in classification, if it is binary, you need one neuron with sigmoid activation. If it is a multi-class classification, you need the number of class is equal to the number of neurons in the output layer, and we have to use softmax as the activation function. Okay. Other loss functions are there. Hinge loss is there. Kehl divergence loss is there. So if you have interest, you can go through it. Okay. So here also we call this as forward pass. Just pass this input, pass through these layers. We got the outputs. Then softmax, you got the predicted output. You have actual output, and use this categorical cross entropy loss to calculate the loss. So you'll get this. This whole process is called a forward pass. Is it okay? Now question is, what comes after the forward pass? So we got the forward pass, we calculate the loss. Okay, and question is, we have to update the W so that the loss will be minimum. So for that, what we need to go backward by adjusting the weights so that it is going to reduce the loss. So question is, how we are going backward and how to update the WH. That is our objective, and that updating W, we call it as a learning. How will do that? Let's see. So again, we are going back to our first function. So let's say this is the function we have. We have three feature values fixed. W is there, and you got y cap. We want to find W such that our function y cap, function output y cap, matches the target value or come as close as possible to our target value, that is 10 here. Okay. So already we have done manually. So we have tried a bunch of values, and we got for 3.2, this is a minimum loss. So if we plot W with loss, your loss will be like this. Means W is in x-axis, loss is in y-axis. So for 1, loss is 49. You see, for 1, loss is here 49. Okay, for 3, it is 9. And for 3.2, it is minimum. And similarly, for 4, it is again increasing. Okay, now where it is minimum? So this is the minimum point. This is the lowest loss value. That is the lowest point of the curve. So if you can means visualize a loss curve for the loss function, our objective is to find out this W value where the loss is minimum. Okay. So if you put this W value in this way, let's say I'm increasing the W value, all these values I have tried. and these are the loss values. So when you plot this W versus this loss, you will get this curve. Okay, and where it is minimum? So this is the minimum at 3.5. That means we have to find out this point of W where the loss is minimum. Within this curve, that is nothing but an optimization problem. We have to optimize the loss function for what W this will be minimum. Okay, how to do that? So question is how this W changing will affect the loss. Okay, so let's see. So how we'll do that? Now we have to use the derivative. So use the derivative to measure the sensitivity of the loss with respect to W. That means if W changes, what is the derivative of that loss function with respect to that W? So this derivative is going to give you the direction of this line. Okay. So now if you use this derivative, we can update the W. How will do that? Let's take our what is our loss function. So for MSC, I'm using MSC loss. For MSC loss, the loss function is y cap minus y whole square. I am removing the 1 by n because I am only calculating for one data point. If it is I am doing for one data point, so that is 1 by n is not there because it will become 1 by 1. So it is y cap minus y whole square, and I am finding out the derivative with respect to W. Means that what does it mean? It means if we change W, what will be the change in the loss? Loss is y cap minus y whole square. Okay. So what is y cap? So already know y cap is x into W. So I'm not putting bias here. So you can put also bias, there is no problem. So this x into W. So now if you calculate the derivative with respect to W for this equation, it will be 2x x into W minus y. Okay. Now this is my derivative. Okay. So question is if we got the derivative, now how that derivative will be used to update the W. So this is my update function, update value. How will update? Already I have discussed with you in the ML class that new W equal to old W minus alpha, which is learning rate, and derivative of loss function with respect to W. Okay, so if we put this is the next weight, new weight, and this is your learning rate. Learning rate means how much a step you are taking towards the minimum. Okay, and that will control this updation. The updation new W will be becoming, so from old W we are getting new W, and that updation is controlled by this learning rate. Okay, if your learning rate is bigger, so updation will be much faster. If learning rate is smaller, updation will be much slower. Okay, so if I put this alpha into the derivative is this one 2x into x into W minus y. So let's see. So if x is 3, y is 10, actual y is 10, I am taking the learning rate as 0.01. Okay, what I have to calculate? I have to take initially what I will do? I will randomly initialize the W. Let's say it is 0.5. Okay, then I have to calculate y cap, which is nothing but x into W. Then I have to calculate the loss. Then we will update, find out this updation value. Then we update it using the updation. So for 0.5, this is my loss. For 0.5, the loss is 72.25. So here it is 70. The circle is at 72.25 in y-axis. Okay, and once we update it, the new W will become 1.01. So when I use new W 1.01 with these three values, that is 1.01 is the new W. When I use new W 1.01, the loss again you see is decreasing from 72.25, it becomes 48.58. And the new W again, new W is obtained from the old W, that is 1.43. When I use 1.43, we get the loss again decreasing, that is 32.60. And we are getting new W as 1.77. When I use 1.77, the loss is 22 and new W is 2.05. When I use 2.05, the loss becomes 14.82 and the new W is updated as 2.3. So when we go on doing this, we'll get that W at 3.22, the loss is 0.12, and after that you get a new W 3.24. But we are not going to use it because let's say 0.02 is very close, means it is minimum. So we'll stop here. This W, that is 3.22, is going to be used in the function. So that means this is the process of learning the new W using the derivative. Okay, and this process is what we are descending. We're just going down, down, down and finding out the minimum. Okay, and we call this as gradient descent. So this algorithm is called gradient descent. We are calculating the gradient, that is derivative, and descending against the gradient. That's why we are subtracting. Okay, so it is an iterative optimization problem, and we use this. This procedure is being used in neural network to get the W. Is it okay? If instead of one W, if you have two Ws, means let's say you have two features. So for two features, there will be two W. So, and if you plot the loss function, it will be like this. Okay. So if it is a loss function like this, then same procedure is going to be used. But here, we have to find out the partial derivative with respect to W1 and W, because W1 need to be updated, W2 need to be updated. Previously, there is only one W. That's why we are taking derivative with respect to W and update it using the updation function, updation rule. But here there are two W's. So we have to update W1 and W2. For that, we need to calculate the partial derivative of the loss function with respect to W1 and partial derivative loss function with respect to W2. For W1, same procedure. For W2, same procedure. Okay. So this should give us a gradient, which is a vector of partial derivatives. Okay. So there are two W, so we will get two partial derivatives and we will get two vectors. So one vector with two values, and we can use it. Same procedure can be used. Okay. So so let's see how we can update the gradients. Let's take this example. So what we will do? This is your loss function LCE. So LCE y cap y with respect to W0, we will get one partial derivative to update the W0. With respect to W1, we will get another derivative to update the W1, and for W2, we will get taken another derivative with W2. Okay, so that means it says how much a change in W2 affect the loss. Okay, that derivative will decide. So let's put in different ways. So instead of writing in one circle, let's segregate them into two. So this summation is nothing but x into w. This y cap is sigma h, to show you how actually it is performing the calculation. So now this total circle is becoming two things. One is x into w, that is your aggregation, and this is your activation. And we are getting, after this we are getting h, and after this we are getting y cap, and then last we got the loss. Okay. So actually see what happens. Now a change in W affects H. Okay, if you change W, then H is the output of the first operation, so it will affect H. Similarly, a change in H affects Y cap, and then change in Y cap affects your final loss. Okay, so that means we need to change, if you want to change W's, we need to change Y cap, then H, then we can change W. Okay, so that how will change it? Now very simple, you just calculate the derivative with respect to Y cap, the loss function of the loss function with respect to Y cap, then the Y cap with respect to H, then H with respect to W2. Okay, and lastly, you just multiply all these derivative, you will get the final gradient of loss with respect to W2. This is nothing but the chain rule of derivative. So what I need actually finally I need the derivative of or partial derivative of loss function with respect to W2. So partial derivative of loss function with respect to W2 goes through these three steps. So we have to calculate these derivatives, multiply them, then we'll get the final partial derivative with respect to W2. Okay, let's put it here. So this is my derivative. You can check how to get the derivative. This derivative already I have calculated. So if you see in forward pass, if the value is 2 and 3 and initialized, I have randomly initialized the W's 0.1, 0.2, 0.3. When it pass through, H will become 1.4, then Y cap will become 0.8, and your loss, if Y is 0, the loss is 1.62. And this is the loss function, this is the sigmoid function. Okay, now let's calculate the derivative. So these are the derivative. Del LC by del Y cap, this is the derivative, Y cap minus Y divided by Y cap into 1 minus Y cap, and derivative of sigmoid is Y cap into 1 minus Y cap. You can check. This is simple derivative calculation. Okay, so now you put the value. So when you put the value, this derivative will become 5.06. This will become del Y cap by H will become 0.16. This will become 3. And if I want to find out del LC by del W2, Then you just multiply all these 3 into 1.6 into 5.06, you will get 2.43. So this is the gradient of W2, that is 2.43, and this 2.43 is going to be used to update the W2. Okay, similarly for W2, similarly you can calculate for W1 and W0. So for W0, same way you calculate, it is 0.81. For W1 it will be 1.62, and for W2 it is 2.43. Now this is the gradient vector, that is 0.81, 1.62, 2.43. So we have to update it. So you see this yellow thing is actually repeatedly, you don't need to do it, because these things are repeatedly calculating for every W0, W1, W2. So once you calculate, you just cache it in memory, then automatically only thing you need to calculate is these 3, and you can automatically find out that. Okay. So we call this process as back propagation. That is chain rule with dynamic programming. Once you got this, then you use the updation rule to update this W0, W1, W2. What is W0? Already W0 will become new W0 will become old W0, that is 0.1 minus alpha is 0.1 into 8 into 0.81. You get new W0. Similarly for new W1 you will get the same, and W2 will get the same. Okay. So this is the updation. So just do, this is 0.1, 0.2, 0.3 old W minus, this is the learning rate, and this is the gradients what you have calculated. So you just update it, you will get a new W. So previously W0 was 0.1, after one iteration it becomes 0.09. The previously it was 0.2, now it is updated to 0.18. Okay, and this 3 becomes 0.28. Now you pass this 0.9, 0.18, 0.28. Again you do the same process. Age becomes 1.29, y becomes 0.78. Now your loss, previously loss was 1.62. Now for new w's, your loss is lowering, that is 1.53. Again you do the same process. So this process, forward pass, back propagation, and gradient descent, you just repeat it multiple times until you reach your solution. Means either you reach your maximum number of iteration, or you have a threshold. So when it below threshold, you stop and you will get the final W. So this is called neural network learning. Is it okay? See, if you have multiple layers, same chain rule is going to be applied. Okay, just check it. Okay. So actually what really happens? So here actually we are doing searching for transformation to map features, that is x to y. Okay. And weights are adjusted to emphasize or de-emphasize the features as needed, so that we get the appropriate weight. And what are the W's? These weights are called knowledge. But we don't know what are these knowledges. This is generally the NN neural network is a black box. But this W, to learn this W, we call this W itself contains some knowledge. And this W is also called parameters. Remember. So always parameter means these weights. So in neural network, if it is a simple neural network, so you have only 9 or 20 weights. But nowadays, bigger neural network have billions and trillions of these W's, which is need to be updated in this fashion. That is forward pass, then go on back propagation, calculate the gradient, then update. And you just go on doing this repeatedly, so that you will get the final W. Okay. So this is your neural network. Let's see the demo. Is there any question? Anyone has any question? Okay. So let's see
any
how
questions?
we can
Ask the question. If you have doubt, ask the question, because you have to implement everything.
So this is the basic thing. Until and unless you understand this, it's difficult to implement. Okay. So
you can unmute. You can unmute yourself now. I have already given them permission. You can ask the question. Okay. If anyone wants to ask the question, you can.
Okay. So yes. In CC, why did we ignore the Y part? So in categorical cross entropy, you see, we are converting the original output into one-hot vector. So in one-hot vector, you know that only the value which is present, that position will be 1, rest are 0. Even if you multiply 0 with anything, it will become 0. So that's why we are ignoring. We don't need that y. Okay, only the positive part means that a positive example that we are taking, the negative y we are not. Okay, so let's any other question? Let's quickly see the implementation. Okay, is it visible?
Yes, yes.
So but what we'll today do, we'll use a TensorFlow. So TensorFlow is a library which has many inbuilt functions available, methods available, classes available to create neural network and all other advanced implementation. Okay, so let's do it. So how we'll do that? So remember few things. First is input shape. So your input shape, input means, you see, when we want to create a neural network, we have layers. First is input layer, then hidden layer, then output layer. Hidden layer can be one or more, but input layer, output layer must be there. So your input layer it will take a shape of input. What will be the shape? Now the number of features what you have, that will become the shape. Okay, and in hidden layer, this is minimum one neuron you can create, minimum one hidden layer you can create, or many hidden layer you can create. And the neurons in hidden layer, it is up to you. You decide. Okay, and these are called hyperparameters. And output layer, always one if it is binary classification, and if it is multi-class classification, that will be the number of classes. If number of classes is 4, so there will be 4 neurons, and number of classes will be 5, there will be 5 neurons. In binary classification, if you are using one neuron as the output, use sigmoid as the activation. If it is multi-class, use softmax as the activation. We have discussed. And for loss function, remember, for binary you have to use binary cross entropy, and for your categorical sorry, for multi-class you have to use categorical cross entropy. These functions are already implemented, and they have present in tf.keras.losses for binary cross entropy, similarly categorical cross entropy. And to optimize that gradient descent algorithm, that optimization algorithm, we can use different optimization algorithms. And the algorithm what I have discussed is called batch gradient descent. Okay, and there are many other versions of gradient descent available, but the most famous version of gradient descent is called adam. So we'll use adam, that is an optimizer. So your optimizer is adam. Optimizer is nothing but this optimization algorithm, which is nothing but a improved version of the gradient descent. Okay, so let's do one thing. So first you just import TensorFlow as a tf. Okay, so and here I am printing the version. Currently it is 2.20. Now let's create a data set. So here I have created a simple data set using scikit-learn's data set called make circle. I am creating 1000 samples. Okay, and the data set will be like this. You just create it, and this data set has x has two values, means there are two inputs, two features. One feature is this one, another feature is this one. Already it is a numeric form. Okay, and y is either 1 or 0. So y is either 1 or 0. So that means for first input y is 1, for second input y is 1, and like this. Okay, so the data set is ready. X is input, y is my output. Okay, so I am putting the data set in a data frame. So let's create a data frame. So this is my data frame x0 x1, and this label is 1 1 1 0 1 0. It is like that. And if you want to calculate how many 0 and 1s are there, so 501 500 0, so it is perfectly balanced data set. Okay, so if you visualize the data points, you see this is my data point. That means I have two class, yellow is one class, and red is another class. So I need a boundary, decision boundary, which will segregate the two class. So here a line cannot segregate it. We need something called circle type thing. Okay, so for that we have to use some good activation function. Otherwise, it will try to always fit straight line. Let's see how it is doing. So first what I am doing, I am segregating X and Y. So here X has two features, 1000 rows, two features. Y has only 1000 values. Okay, this is the length, 1000 are there. And if you want to see what is X0, Y0, so X0 is this two value and its corresponding Y0 is 1. Okay, now this is important. How will create a model? My data set is ready. How will create a model? So to create a model, first you create a model using a functional and sequential API. So there are two APIs available in TensorFlow. One is sequential API, very simple. Another is functional API, a little bit tricky. It's not that much difficult. But here, for our purpose, we will use sequential API. Once you create a model using sequential API, next step is to compile a model. When you compile, you have to pass what will be the optimizer, what will be the loss function, you have to give that. And then you train it using fit method. These are the three steps. Remember, in every where in the TensorFlow, when you want to create a model, first you create a model using either sequential API or functional API. Once model is created, then compile that model, second step. When you compile, you have to pass the optimizer, you have to pass the loss function, you have to pass which metric is to be used for performance measurement. Third step is to train the model, means fit. So fit the model on your training data set. These are the three steps. Okay, so let's do. So now what I am doing here, I am calling a sequential API. So to do that, tf.keras.sequential, just call it, and within this you just pass the layers. So how many layers? Let's say I want to create only one input layer and one output layer. So here input layer means you have to use tf.keras.layers.input, and in input you have to give the shape. What will be the shape? Because the number of features you have here, I have two features, so the shape will be 2 comma, because only two features are there. It is not a matrix, so it is only a vector. That's why 2 comma. Okay, and one output. So for output layer we have to use dense. So dense layer is actually creating a dense connection with this neuron of that layer to previous all neurons in that previous layer. So here I have only one neuron. Okay, now my model is ready, and I am storing that model in model_1. Next step is compile the model. So model1.compile. Here you have to pass the loss function. So loss is loss equal to, everything is available, just to pass it. tf.keras.losses.binary cross entry, because it is a binary classification problem. And what is optimizer? Optimizer is tf.keras.optimizer.sgd. Here sgd is we are passing, and metric is accuracy. Okay, once it is compiled, next is to call the training method, that is fit. So model_1 dot fit x y epoch. Epoch means how many times this training will be done on the total data set. That means 5 times it will go through the total data set. Okay, so let's run it. So when you run it, you see, so this is epoch. So accuracy is 48, loss is 6.4. So means this binary cross entropy loss is this one, accuracy is this one. And after 5 epoch, only 51% is the accuracy, and this is the loss. So it is not a good model. Okay, and if you want to find out evaluate it, it will give you same, just model.fit, it will fit it, and model.evaluate will be evaluated. Let's say instead of 5 we are going to do 200. Even if you do for 200 epochs, still it is not going to give you good result. Why? Because you see here we have not used any activation function, we are just passing one. So one means we are not passing anything in the activation function, only it is aggregating, no activation function is allowed. That's why it is trying to learn a single means straight line. So when you use a straight line, obviously it needs a circle to segregate these two classes. So straight line cannot going to give me good result. Okay, so even after 200 epochs, still it is giving only 47%. Let's modify it. So one modification is you can increase the layer. Okay, another modification is you can use the different activation function. So here I have used another layer. So tf.keras.layers.dense, you can tf.keras.layers.dense. Two dense layer I have used. Okay, so you can also this one is nothing but the neurons, number of neurons. you can increase the number of neurons in that layer. That up to you. Okay. So even if you change it, still it is not going to give you good result. So what I need, I'm just going to the final model because there is no time. So you see, this is another way. Another model I have created. So input is same to here in first dense layer, 100 neurons are there. In second dense layer, 10 neurons are there. That means there are two hidden layers. First hidden layer has 100 neurons. Second hidden layer has 10 neurons. And the last output layer has only one. And if you again you do this, still it is not giving me good because still now we have not used your activation. Okay, so let me directly go and use the activation, then it will be easier for you to understand. So see, without using activation, this is my learning. A straight line is learning like this. It is cannot segregate yellow to red. So for that, what we can do, we can use an activation. Let's see which activation will be good. This one. Just a minute. Just directly I'm going to, yes. So you see this one. So this is one good model. You see in sequential API we are passing the layers, and here I am not only passing the number of dense neurons, also I am passing the activation. Here I am using ReLU for the hidden layer activation and sigmoid for the output layer activation because sigmoid is required. So when you run this, you will see now the accuracy is 81%. Previously it was only 60%. Okay, and if you try to plot it, it is trying to segregate like this. Okay, so this is the way you can create a model. Very simple. What you do first, you create the data set, or if you have data set, import it into data frame like you are doing in the NLP case, that you just segregate train and test split. Now for training, you just create a model. And how you create a model? Model creation here has only 3 steps. First, you use a sequential API, pass the layers, pass the values in the dense layers, how many neurons you need, what are the activation function. And you know that for hidden layer, activation function is generally ReLU. For output layer, it is sigmoid if it is one output. If it is multi-class, you use softmax. Instead of sigmoid, you use softmax. Then compile it by passing the loss, optimizer and metric. Then you fit it. This is the only 3 steps. Okay. So I think this much. Other things are there here. I will share it so that you can go through it. Everything is written here carefully, so you can go through it. And if any doubt, you can ask. Still, is there any doubt? Anyone has any doubt? What it is in MSc and C? Is it compulsory that the value of n, that is number of neurons in the layer, and when will the value of n will be different? What is that n? Number of neurons. You see, mean squared error is used in the regression when you are predicting some real value like house price prediction. In mean squared error or in a regression case, only the last layer will contain only one neuron. But for classification case, if it is a binary classification, you have to use one neuron at the output with sigmoid activation. If it is multi-class classification, you have to use number of neurons is equal to the number of classes present, and you have to use softmax. Okay, so n will vary. N is not same. N will vary depending on the type of problem you are dealing. Is it okay, Shreyan? Any other question?
You can unmute and ask the questions. And
during fitting, you have passed another parameter as verbose along with the epoch. So okay. So that verbose that is not that much important. Verbose means, you see, when we are training, the epochs are printing. Epoch 1, epoch 2, epoch 3, epoch 4, like this it is printing. If you do not want to print, means this process, if you do not want to print, you put verbose as 0. By default, verbose is true, that is 1, and it is printing. And if you make verbose as a 0, it is not going to print. Are you getting at what I'm saying? Is it okay? Verbose parameters only job is to just show or not show the progress of the training. Okay, which we are printing. Okay, another question is, so how do we decide the value of n? N is the number of neurons in which layer you are asking? In the hidden layer or in the output layer? Srayan, in which layer you are asking? Whether it is you are asking for hidden layer number of neuron or the output layer number of neuron? Okay, so for hidden layer, there is no formula. Nothing is that is up to you. So you try many different combinations. Okay, so if you and one very simple idea is that if you take more neurons in the hidden layer, the model will become complex and sometimes it will overfit. In that case, you have to change the number of neurons to small. But in the output case, it is always defined. It is fixed. In output neuron, how many neurons you should use? If it is a regression, you have to use one neuron. If it is a classification, there are two possibilities. Check what type of classification problem you are dealing with. If it is a binary classification problem, that is whether spam or not spam, whether it is a male or female. So if it is a binary classification problem or two class classification problem, the number of neurons in the output layer is always one. You can take two, but just think now it is one, and one with sigmoid activation function. This is fixed. But if you are using multi-class classification problem, let's say your problem is identifying whether you are getting grade A, B, C. There are three class classification problem. So for that, you have to use three neurons in the output and their activation function will be softmax. This is the rule. Is it okay? Yes. Any other problem? You just go through it. Okay. It will be easier for you to understand. Even if you find any difficulty, we will discuss. Because in the tomorrow session, we will discuss how these things will be applied in NLP. Start using another embedding technique that is called word to vec. That we will discuss tomorrow. And we will see one classification problem on that. Okay?
Okay then. Just practice it and sir will share this thing today with you. Fine.
Today I will share it. You just go through it.
So now sir, only here 35 to 40 students are joining. So among them only we have to find out the good students. Okay. So we'll give the assignment. We'll concentrate on good students, those who are attending.
Yes, sir. Yes, sir. Once they understand this part, because writing program is very easy. You just see only 4 or 5 lines of code is required. So don't worry about writing code. Only try to understand what are the steps and how to write. This much is required. Okay. So we'll deal with that. Don't worry. If you have face any problem understanding the code, you just ask me.
So in from today only, I am sharing this brochure of the NLP workshop, low resource NLP workshop. So the details of the resource experts I have already shared in our group. Okay, you can find out from there. So from there also you will get lots of problems. I have also asked to Nayan sir also, he will join and see the resource persons. Okay, all are 3 to 4 are from outside India, and others 2 from IIT, IIT Patna. Then Duet from my IIT Madras also one of the professor is there who is of not from the technical background. Okay, so lots of resource persons are there. They are going to tell about their research problem and what are the future problems on that we can work. Okay, so from here only we have to find out minimum 10 to 12 or 15 to 16, 20 problems we are going to find out from here. And along with the answer, they are also going to associated with you and help you. Okay. So be ready. So before that one, whatever things we are covering, you just try to implement those things and ready yourself for the coming workshop, low resource NLP. Because in rich resource languages, many works has already been done. Now, same thing if you are going to learn everything, whatever teacher is covering, the same thing we are going to apply in the low resource. So easily we can publish a paper or we can go for some proposal, research proposal. Okay, so whatever things covered by the answer, you just go through that one and tomorrow sir will cover another this classification this web back, no sir?
Tomorrow is another
Okay.
important concept to
Okay,
cover.
back. Okay then.
Okay,
For
sir.
today this much. Again tomorrow we'll meet at the same time. Thank you.
Thank you, sir.